All right, let's get into it. For decades, the whole dream of fusion energy has been about one thing: creating a star in a jar. We're talking about taking plasma, heating it to temperatures hotter than the sun, and then trying to cage it with magnets. But here's the thing: the real challenge isn't just getting it hot, it's keeping it under control. This stuff is so unbelievably violent that it can literally destroy a multi-billion-dollar reactor in the blink of an eye. So the question is, how in the world do you tame it?
So here's how we're going to break this down. First, we'll look at the core problem, fusion's unstable heart. Then we'll dive into a whole new way of thinking, called the typed tower of governance. We'll see how it uses something called deterministic receipts for verification, look at the proof architecture behind it, and finally, talk about what this all means for the future of fusion energy. You see, the single biggest hurdle for commercial fusion power isn't just hitting those crazy high temperatures. Nope. It's the ever-present threat of these violent instabilities that can cause a total loss of control and shred a reactor in just milliseconds. This is the problem of plasma disruptions.
And this, right here, really paints the picture. On the left, that's what you want to see: a healthy, stable plasma. It's all organized into these nice, clean, nested magnetic layers that basically hold all the heat in. But on the right, that's what happens when things go wrong. And instability kicks in, and those layers tear apart and reconnect. You get these chaotic magnetic islands, which are basically just holes in your magnetic bottle, letting all that precious energy pour right out.
And that leads us to the official term for this nightmare scenario, a plasma disruption. And let me be clear, this is not some small glitch. It is, without a doubt, the most serious threat any tokamak can face. A single one of these getting out of hand in a massive reactor like ITER, well, it wouldn't just end the experiment, it would be absolutely catastrophic.
And it's not like there's just one bad guy here. You've got a whole list of usual suspects. There are sawtooth oscillations deep in the core, which can plant the seeds for much bigger problems. Then you have neoclassical tearing modes, or NTMs, which are a major cause of disruptions. And then there's the big one: vertical displacement events, or VDEs, where the entire plasma column just says, "I'm out," and slams into the reactor wall. The really scary part? They're not isolated events. One can trigger the next, creating a cascade that leads to total failure. Now, don't get me wrong, our current AI controllers are getting really, really good at spotting and reacting to these things. They can prevent disruptions a lot of the time. But that brings us to the billion-dollar question, doesn't it? Can we get beyond probably safe? Is it possible to build a system that can formally prove, with absolute mathematical certainty, that it will always keep the plasma safe? That is the mission here. And that's where the Coh Fusion Program comes in. This is not just another fancy algorithm. It's a completely new way of thinking about reactor safety, and it's built on a new architecture they call the typed tower of governance. This chart really shows you the whole idea. The typed tower is basically a bridge connecting the infinitely messy, complex physics of the real plasma to the clean, deterministic world of a computer proof. It starts at the bottom with the raw physics. Then it moves up to what our sensors can actually measure. From there, it defines a strict, mathematically proven safe zone. And at the very top, it creates an unforgeable record, a proof that the system never ever left that zone. Now, at the heart of all this is a concept called a coherent object. The best way to think about it is like a perfect digital twin of the entire reactor system. And this is the key insight. We stop treating the tokamak like just a physical machine, and we start treating it like a formal mathematical object. It's defined by every single possible state it could be in, a function that tells us how close it is to danger, and a verifier that checks every single move. Let's drill down on that middle part, the violation functional, because this is just brilliant. Think of it as a digital guardrail. It's a single number that gives you a distance to disruption. If that number is 0, you're perfectly safe. But as it starts to climb, you know you're getting closer and closer to the edge. The entire goal of the control system is to do whatever it takes to keep that number from crossing a critical line. And this quote just nails the whole ambition of the project. The goal here is to build an unbreakable, mathematically explicit cage around the plasma. It's a cage that's not made of steel, but of pure, cold logic. Okay, so you've got this mathematical cage, but how do you enforce the rules? How do you make sure nothing ever breaks out? Well, the answer is a beautifully simple idea: deterministic, verifiable receipts. This is what they call the no bluff rule. This right here is the golden rule of the whole system. Every single action the controller wants to take, every little tweak to the magnets,
has to come with a receipt, a piece of verifiable data. If the verifier can't check that receipt and give it a green light, the action is denied. That's it. Period. No exceptions. No bluffs allowed. This slide just lays out the whole paradigm shift perfectly. We're moving away from the old way of doing things, probabilistic AI, best effort control, which is basically a very smart guess, and we're moving into a new world that is deterministic, verifiable by receipts, and, because of all that, provably safe. It's the difference between crossing your fingers and hoping for the best versus proving the worst can't possibly happen. So you might be thinking, okay, that sounds great in a perfect world, but what about reality? Magnets take time to respond, sensors have noise. Well, this is where Coh Fusion gets really, really smart. It doesn't pretend those problems don't exist. It actually prices things like actuator latency and sensor noise directly into the safety proof itself, as part of a defect budget. So think about it like this. The system treats any gap in its knowledge, any delay, any bit of noise, as a quantifiable defect. Every millisecond of blindness due to latency costs something from its safety budget. Every control action is a spend from that budget. In this world, safety has to be explicitly paid for, which guarantees the system can never write a check that its hardware can't cash. So how is all this actually being built? Because this isn't just a cool idea on a whiteboard. It is a massive, ongoing mathematical undertaking. The whole point is to construct what they call the canonical spine of plasma control. You can think of it as the unshakable, logical backbone that holds the entire safety system up. And this diagram shows you that logical flow. You don't need to be an expert in category theory, but the key takeaway is how it's built from the ground up. It starts with the purest of math, and then rigorously stacks layers of physics and engineering on top. Each and every step has to be proven before the next one can be added. That's how you know the entire structure is sound, from the most abstract concept all the way down to the final command that zapped to a magnet. And I think this is fantastic, because it shows real intellectual honesty. The architecture uses these tags to be crystal clear about the status of every single claim. Some parts are fully proved. Others are proven by connecting them to an already solved problem. But crucially, it also flags where a lemma needed, where they need help from the wider physics community, or where something rests on a foundational assumption. That kind of transparency is how you build trust in a system this complex. So when you zoom out, what does all this really mean for the future? Well, we're talking about nothing less than a fundamental change in how we even approach fusion energy. We're moving from what has always been, at some level, a highly educated gamble to a truly verifiable system. And this quote brings it all home. When we're talking about plugging a fusion reactor into the national grid, it probably won't break is just not going to cut it. That's not an acceptable engineering standard for the future of energy. For a commercial power plant, you need something better. Provable safety isn't a luxury, it's non-negotiable. So let's just quickly recap the big paradigm-shifting ideas here. 1. This system is verifiable by design. Safety isn't bolted on at the end, it's baked in from the start. 2. It treats real-world hardware limits as a defect to be managed, not a problem to be ignored. 3. It's compositional, meaning you can manage a whole zoo of different instabilities all in one unified framework. And finally, it's being built open source to get everyone around the world pulling in the same direction. Which leaves us with one final and, I think, profound question. We've made unbelievable progress on the physics of fusion, but maybe, just maybe, the final key that unlocks commercial fusion power isn't another physics breakthrough at all. Maybe it's a mathematical one. A provable, verifiable license to operate that can finally give us the confidence to safely operate a star here on Earth.